All right, so this presentation is on the 4 states of matter. All right, we're going to look at solid, liquid, gas, plasma, a little bit about phase change. And this is going to introduce to us the idea of how we look at molecules. All right, so here we go. I'm going to grab my pen. And we will be, oh, just a second. Let me get this thing squared away. All right, there we go. So 3 states of matter you are probably already familiar with are the solid, liquid, and gas phases. In chemistry, we're also going to talk about the 4th state, plasma, okay, and what that is. So basically, the state of matter, when you really describe it as how the molecules are behaving, is based on how they're arranged, based on how the particles are moving, based on the distance between the particles, based on how much energy the particles have, right? How fast they're going or how slow they're moving. And it's, the combination of these 3 things that give us our 4 different states. Now, this depends on your understanding of something that might be new to you. It's called the kinetic theory of matter. And basically what it says is this: all matter is made up of particles, right? And when we say particles, most of the time, you should read that as atoms, okay? And they are in continual random motion. They bounce off of each other, they stick to each other, they interact with each other. Sometimes they don't interact with each other, but they are always moving, no matter what, all right? When we measure temperature, what we're actually measuring is the movement of molecules. So the kinetic molecular theory, all right, or the kinetic theory of matter is really important that we understand. So, from PE, right? Kinetic means movement. All right. The movement theory of matter, right? Molecules are moving. So how are solids moving? Well, solids are really tightly packed. They vibrate in a fixed position. They don't go far, all right, but they do actually move. And you can see here, there's just very little movement, all right? And they have a definite shape, and they have a definite volume. Their shape doesn't change because they're in a fixed position, right? So because they're fixed, the shape is unchanging. It's defined. Same thing with the volume, okay? It's going to displace the same amount of, space no matter where it sits. A cube is a cube is a cube. If that cube is 1 centimeter on each side, then it's going to displace 1 cubic centimeter worth of air or water or whatever medium you put it in. So that's a solid. All right. If you heat a solid up, you can melt it, right? You turn into a liquid. And so the particles in a liquid are close, but they're not quite as close, okay? And they have a little bit more room to move around. They have more energy, so they can kind of break the bonds, some of the bonds of attraction between them, and they slide past each other. Liquids don't have a defined shape, right? We know that water will take the shape of whatever container you put it in, but they do have a definite volume, right? If I have, 1 graduated cylinder, right, that is this big, and it's got 50 milliliters in it, and then I grab a beaker out of my cabinet, and I take this water and I pour it in there. Well, how much water am I going to have in there? Well, obviously, I'm going to have 50 milliliters. Now, even though they don't look the same, right, because they have an indefinite shape, they've taken the shape of their container, the volume did not change. On both sides, it's 50 milliliters, okay? Well, how do we go from a liquid to a gas? Well, pretty obvious, right? We heat it. And when we heat that liquid, we give it more energy, and the particles spread further apart. They're much more energetic. They, hit each other and collide. You can see here in this animation that every other gas particle is bumping into each other and coming apart. And the thing about a gas is a gas has both an indefinite shape and an indefinite volume. So if I have a box, right, like a cube, and it's full of O2. Well, the volume, let's say it's, we'll say a meter by a meter by a meter, right? So I have 1 cubic meter of O2. Okay, and the box is shut, right? It's got a top on it. Well, if I open that box, right, and the oxygen goes out, right? So I've opened the box, the O2 now leaves. Well, it's actually going to expand, and it's going to take the shape of its new container. If that new container happens to be the Earth, it's going to spread out, and all those molecules are going to diffuse as far apart from each other as they can. And so I can no longer say I have a cubic meter of O2. I've now opened it up, right? And that gas just spreads out and spreads out and spreads out. If you want to turn a gas into a plasma, well, the trend continues, right? We're going to heat it. And when you heat it, right, we start to actually mess with the electrons in the gas, and we'll talk about that in a minute. But let's kind of look at our simple phase changes. So if I go from solid to liquid, I'm melting something. Heat goes into the solid as it melts, all right? And so the solid is absorbing heat from its surrounding. The molecules in the solid are, becoming more energetic. They're starting to vibrate faster and faster and faster, and eventually they go from a solid to a liquid. That's melting. If I go from a liquid to a solid, then I'm freezing, and the heat is going away from the liquid. So I'm pulling heat out of the liquid. And when we say heat, we're talking about energy. Those two things are interchangeable terms, all right? And if I want to freeze something, right, I need to get the molecules to slow down. I need them to have less kinetic energy. And so I pull heat out of them, right? I have to get it to go somewhere else. If I want to go liquid to a gas, we call that vaporization. Now that includes both boiling and evaporation, right? So the word vaporization just means liquid to gas. That could be boiling and evaporation, right? Same thing. Same thing if we're looking at the heat is going to go into the liquid as it vaporizes. So think about if you sweat, right? I have a droplet of sweat on my skin. I want the sweat to cool me off, so I need it to evaporate. So the heat from my muscles go into the water, into the sweat, and the sweat absorbs enough energy for me to turn into a gas and evaporate. Well, that removes the heat from my body, right? And turns it into the energy needed to evaporate that sweat. So that's vaporization. If I go gas straight to a liquid, all right, skip the we're going backwards now. We're condensating, right? This is how you make a cloud, right? Water vapor in the air cools down, forms water droplets, which makes a cloud. Heat is leaving the water vapor as it condenses. If I go solid to a gas, I'm sublimating, all right? Sublimation is going from a solid straight to a gas, all right? And that would be heat going into the solid, okay? It's skipping the liquid phase. Now, if you heat something up really, really hot, it doesn't just stop at a gas, right? You just have the superheated gas, right? Something like 1 billion degrees Celsius. Well, it actually turns into a plasma. And a plasma is an ionized gas. And you can see in this picture, all right, these little guys here, these are my electrons, and here is my atom, all right? But when an atom has a charge, we actually don't call it atom anymore. We call it an ion. An ion, all right, this is an atom with a charge. And it's positively charged because it lost its electron. And so plasmas are really good conductors of electricity. And because they're charged, they're affected by magnetic fields. So they're very similar to gases, but they're not quite the same, right? Most gases are inert or at least not charged, right? So if I have a gas and a magnetic field, there's nothing to make the gas respond to that magnetic field. Now, because they're like gases, they also are defined as having an indefinite shape and an indefinite volume. So very similar to a gas, it's just been ionized. This is the key there. And we find plasmas in a lot of places. Like lightning is plasma. The sun, right? All the stars are, big balls of plasma. And we'll talk about that a little bit more in a minute. So if we put the 4 states next to each other and we look at how much energy they have, we should notice that there is a pretty regular transition going on here. solids have the lowest amount of kinetic energy. So a solid has low kinetic energy, but it does have high potential energy. A plasma, on the other hand, has really high kinetic. And so we would obviously say that it probably has a low potential energy, right? It's moving very rapidly. Solids are tightly packed, right? That's something we want to know. Gases are well separated, right? They get as far apart as they can from each other. Liquid is just kind of in the middle. In order to go up any of these ladders, we have to add energy, okay? So we're adding energy to go up. If we want to go down, obviously we want to remove energy, okay? So if I'm going, from a gas to a solid, I need to pull energy out of my substance. If I'm going to go up from, say, a solid to a gas, I need to add energy to my substance. Now, some places where we find plasmas, right? Flames, those are plasmas. Really common misconception that fire is a reaction. Fire is not a reaction. It's the product of a reaction. It is a plasma, okay? Lightning is a plasma. The aurora, like the northern lights, are plasmas. And the stars, all right, are big balls of plasma. We'll talk about that in a second. Now, there's a couple videos I've embedded in this this PowerPoint I want you to watch. The first one is from Lake Maracaibo, and you can. I'm gonna mute this and just talk for a minute. This is from the Weather Channel. Lake Maracaibo is one of the places in the world that gets struck by the most lightning anywhere. All right, so it's pretty wild. And I just want you to watch this. It's in Venezuela. Give it a watch. It's pretty interesting. It's about the people who live on the lake and this guy who photographs the lake and watches the lightning. And we'll kind of fast forward here to a couple of the good parts. Let's see. There we go. And when it lightnings here, it lightnings a lot. Okay, so an interesting place, right? It's a real world connection to plasma. And I'll let you guys watch that kind of on your own. All right. Another place is Catatumbo. And this YouTube video that I inserted, it's old. It doesn't work. But if you look up the Catatumbo Storms, you'll get to see, like this picture, like the thumbnail has, quite a bit of lightning. All right. Another place that we find the aurora is the northern and the southern lights, because there are northern and southern lights. It's not just a northern thing. And you can see them from the space station really, really well. And what's going on here is the sun, the solar wind that comes off the sun is full of ionized plasma. And when it gets near the Earth has a magnetic field. And so it follows the magnetic field lines down to the poles. So if I kind of draw a picture here, I'm going to have to pause the video while I do this. Let's see. Yeah, okay, let me draw a picture. Nope, is it not going to let me draw? All right, well, never mind. Basically, you have the Earth. It's got a magnetic field that goes from the North Pole to the South Pole. And as the solar wind comes in, it rides that down towards the poles. When the solar wind hits the atmosphere, there are reactions that are occurring, and you end up with the northern lights, okay? Very interesting, very beautiful. You can see some lightning there too, but watch this video. It's got some nice music. There's no talking or anything like that. But when you watch this plasma, you can see, especially in this view here, those like snaky lines. Those are our magnetic field lines, and they're just following them, okay? So plasmas are impacted by magnetic fields, okay? So you can watch that video on your own. Another place that we find plasma is the sun. This is from NASA's, I think it'll say it here in a minute. It's like the heliophysics lab. Yeah, and helios is the sun, right? It's where we get the word helium from. And this is just a video of a medium-sized solar flare that they got on camera from one of their observatories. All right, so let's watch this thing. I'm going to pause it when we get to a certain part. So let me go. So the sun, all right, also has magnetic field lines. And let me get to where puts the Earth. There we go. There's the Earth for scale. All right, so we'll just leave right here for a minute, and I'll give you some info. So stars are ginormous, obviously, from this picture, you can see that, collections of gas. And a star is a constant battle between gravity and heat. So the gravity pulls the gas together, and the weight of the gas pushing down on the core of the star heats it up, right? More pressure, greater heat. Well, the heat, right, as you know, these atoms of gas are pushed together so closely that they touch, it produces a tremendous amount of heat, right? We get fusion. And that heat causes the star to expand, right? So you have these convection currents of hot gas rising from the middle, gravity pulling the star together, and this ionized substance gives off all these wild magnetic lines, and so they just ride the magnetic lines, and that's what a solar flare is. So stars are really, really cool. There's a lot of chemistry that goes on in the stars. Then we'll look at those a little bit more later in the year when we talk about Joseph Fraunhofer, all right? But you can watch these videos, kind of get an idea. To give you an idea of the temperatures going on here, if we look over here on the right, this is the temperature in Kelvin. Right? Kelvin is Celsius plus 273. And these numbers here give you an idea of how hot some of these objects are. So like the core of our sun is pretty warm, right? 10 to the 8th degrees. That's hot. I don't know if you're aware of that, right? So later in the year, we'll look more at the math that goes into some phase changes. Right, but because we're going to be looking at a physical chemical lab here soon, I want to make sure that we talk a little bit about a phase change and what it is. So basic definition you should know from middle school. A phase change is when you go from a solid to a liquid, or a liquid to a gas, or a gas to a plasma. It is a physical change, all right? You're only affecting the appearance. You're not affecting chemical makeup, right? It's reversible. And any change to a chemical that is reversible has to be a physical change, right? It's not a chemical change. When you have a phase change occurring, right, you're either releasing heat or you're absorbing heat. Which way you're moving up and down that graph that had, like solids, then some energy, right? We're going up, liquids, then we have some more energy, gases, then we have some more energy, right? And plasmas. If you're going this way, you are absorbing heat. If you're going down, then you're releasing heat, okay? And that's really what's governing the phase change. That heat energy, is transferred based on the molecules touching or not touching or how fast they're moving. If you are releasing it, they're slowing down, they're getting closer together. If you're absorbing it, they're absorbing that energy, they're moving faster, they're getting further apart. Now, you can kind of remember the phase changes as a triangle, right? We leave out plasma because plasma is like, off from an offshoot of the gas state. So there are, two-way streets between each of these phases. You want to know those two-way streets, right? So from solid to liquid is melting. From liquid to solid is freezing. I think we probably all know that one. To go from gas to a liquid, we are condensating. If we are going from a liquid to a gas, we're vaporizing. This could be boiling or evaporating. Both are vaporization. If you're going from a gas straight to a solid, that's called deposition, like you're depositing the gas as a solid. And if you are going from a solid to a gas, then you are sublimating. All right. This one over here may be new, but hopefully the other ones are pretty familiar. Now, melting, just to kind of give us some clarity, right? You can look at that as like heating up glass, right? Turning it towards a liquid, or you can look at it as just, ice. There's a lot of different ways you can do that. A couple of videos here for you to look at if you need some reminder. Freezing is pretty cool, right? We're going to change something from a liquid to a solid. Now, when you watch this one, listen. Make sure you have the sound on. All right. So I'll turn this up. Now, obviously, this ball of red hot nickel is not totally melted. It's not a total liquid. All right. But when you drop it in the water, you hear that noise. All right, and make sure that you're watching that as you see what's going on. So literally what's happening is the crystals are forming. They're growing inside that red hot, nickel. So phase changes with metals are really cool. But as he drops it in the water starts to absorb the heat from the nickel, which makes the nickel atoms slow down. They get closer together. And in this case, the metals form those crystals, and those crystals, like pushing past each other, make that audible noise. So that's a pretty cool example of a phase change. Now, vaporization is, changing from a liquid to a gas, all right? And I thought, we could look at a cool video of, water boiling, but even better, right? Let's make it bigger. Let's look at a comet. So on a comet, as the comet gets closer to the sun, it starts to heat up, and that icy comet starts to melt, and then that melt starts to vaporize. So what you're seeing here, this black disk at the top, is blocking out the sun so that we can see, the comet around it. And you'll notice that, I'm going to roll this back, something interesting about a comet, the tail always points away from the sun. So it can actually, the tail can be out in front of the comet, as you see here on the right. And as the molecules absorb that heat energy from the sun, they go from their frozen, icy, solid state out to, start to become a liquid, and then the liquid vaporizes and turns into a gas. Now, a sun-grazing comet gets really, really close, and it can lose a tremendous amount of its icy material in one single pass. So watch this video. It's very interesting. It gives you a little bit of chemistry, a little bit of physics, a little bit of earth science, or I guess space science, all at once, okay? Now, evaporation is a phase change from a liquid to a gas. This can occur at a lot of different temperatures. It doesn't have to be at the boiling point. So if you've ever been out to a lake and you see that like mist coming up off the lake in the morning, that's evaporation. Molecules are speeding up, they're moving further apart, they're absorbing heat energy, usually from the sun, and they are leaving the liquid state behind. If you have a lot of evaporation in a hurry, you can get a water spout. And a water spout is pretty interesting, right? This one's out in the Grand Cayman Islands. And when you have fronts moving in and you have a lot of hot, or a lot of temperature, a lot of warm temperatures from the sun, that water is absorbing that energy. It can start to evaporate, and then it gets kind of twisted in two merging fronts, and you can end up with a water spout. So water spouts can be really dangerous. This one's huge, and when the front kind of moves away, though, it just kind of dissipates and all the water falls back down. Interesting stuff. Condensation, all right, is when gas goes to a liquid form. It's how we make clouds. You get some pretty cool cloud formations that can happen, like nacreous clouds, which we'll talk about. When we talk about the ozone layer, they form at the South Pole. They're like really pretty. Mammatus clouds, which look like someone piped a bunch of icing into the sky. I like, not mushroom clouds, those are bad. These. Let's see if we can get the name up here. I believe it's called a lenticular cloud. Yep, there it is. A lenticular cloud, which like piles up on top of itself, which is pretty cool. And let's see, where's the one? There's the last one. Yeah, these clouds. So a lot of really pretty cool clouds, right? And all of those are forms of condensation. Sublimation is when you go from a solid to a gas. So if you've ever handled dry ice, which I'm pretty sure you can buy at like Kroger, drop that, on the ground and just let it do its thing, and it just smokes and smokes and smokes. Well, if you're not paying attention, you're like, oh yeah, it's just smoking. Well, that's actually really cool because it's going from a solid to a gas and it's skipping the liquid phase, right? So that's called sublimation. Deposition is how you get frost on a window. The water vapor in the air is deposited directly as ice to the surface of a really cold object, like, say, a glass window. And that's going from a gas straight to a solid. And we're going to stop right here. Well, actually, after one more slide. But this is called a phase diagram. This puts everything in terms of pressure and temperature. So we can see that the temperature and the pressure is graphed on the X and the Y axis. So here's our two axes, there's our X and there's our Y. And we can see that there is a relationship between the temperature at which these things occur, these phase changes occur, and the pressure at which they occur. Something that's interesting here, we're going to talk more about this graph later on, but the triple point, every single compound has a triple point, and it is the pressure and the temperature at which the solid, liquid, and gas phase all exist at once. So I'm going to skip forward and just show you this triple point video. And then I know this is not the end of the slides, but it's all the slides we're looking at right now. So this is cyclohexane, and they've got it under vacuum in order to kind of get it to go to the triple point. And you can see that right now it's a liquid, but it's kind of moving as the air gets pulled out of it, and then it just spontaneously freezes. And then while it's sitting there frozen, you're going to notice some bubbles are going to start to appear on the bottom, and it's going to start to boil. All right, and we're going to form a gas. And then that gas, they're going to start to boil, and then the gas is going to recondense. And so this is the triple point. And at the triple point, the solid, liquid, and gas phase all occur at once, which is a pretty neat thing to look at. And every compound, every chemical, every thing that you can imagine has a triple point. Some are harder to get to than the others, but cyclohexane is one that you can actually observe if you have a vacuum pump in the lab. All right. So that's where we're going to stop with this presentation. Now, hopefully this is a lot of review from, some previous science courses that you have. But if you have questions, as always, reach out and ask questions. All right.